Hi, so my name is Jeff Dalton. I'm an associate professor at the University of Glasgow. I work in natural language understanding, conversational search, and conversational NLP. So first, a little bit of information about me. I've worked in knowledge and understanding in industry and academia. I did my PhD at UMass Amherst, where I focused on how we could use search to improve natural language understanding tasks. And then now, in various roles, how we can use knowledge to make search smarter and our conversational assistants smarter. So I also worked on the Google Assistant team. I was there kind of working on response ranking when it launched there. And now I'm back in academia, kind of leading a research group. And we just got some really great work, an acceleration fellowship from UKRI, multi-million-pound grant to really kind of build the next generation of neural information assistants. So please join us in kind of helping to advance these systems. So this is a selection of some of the research that my group has been working on and kind of published recently. So just a little bit of a different spin on some of these. Multi-modal foundation models, not just language, but looking at speech, looking at images, and how we can understand those to make them reason more effectively. I'll be talking about conversational search, kind of what the future of web search might look like. And also systems. I come from a systems background, building systems, deploying them in the world to millions of users. So check out our website there, and there's also links further on. The work that I'm going to be talking about is not just me. It's a whole team here as well, PhD students, and a kind of a growing research lab at Glasgow who are specialized in this. Some of them are looking for internships, and some of them would like to collaborate with external people, so please come talk to me. There's some opportunities to collaborate with us. I wanted to give a shameless plug. We just published a new book. This is a book on conversational information seeking. It covers topics on conversational search, recommendation, question answering, with colleagues from UMass Amherst, Google, and other universities there. We also had a tutorial at SIGIR, one of the leading kind of information retrieval conferences, where we presented that. And most of the materials are available on their website. And we'll be giving that tutorial again at upcoming conferences. So happy to come talk to you further about those. I'm going to ask you to think about the future of assistants. Imagine what genuine assistants might look like. So not just the Google Assistant, but when you actually needed something. What does assistance actually mean? I'm going to give you an example from my experience. This is my son, Aiden. He's now a little bit older than this. He's just turned 1. And this was his first trip to see his grandparents. He went in Michigan in the winter. He got to play in the snow. He had a good time. But as you can imagine, if you're flying in the middle of winter, there's also other issues that go with it. So we got stuck. We got stranded in Grand Rapids, Michigan, trying to get to Chicago. There was a blizzard. It snowed in Chicago O'Hare, which may not be surprising for those of you who have been there. It's a very windy place. And of course, that presents lots of issues. So at some point, they unloaded us off the plane, and 100 people immediately got into a customer service queue, and there was one customer service representative to help us. You can imagine how happy we all were. So this took hours, and what did the first thing that we all did? We turned to our phones. We tried calling customer service. We tried calling Google Assistant. We tried using all those different tools that we had at our disposal to try to solve our problems. And for most of us, none of them worked. Right? They didn't work because we couldn't get through to customer service because it was the holidays. They didn't work because it didn't have knowledge of my flight itineraries and lots of those different tasks. Right? So that we have a long way to go to actually be able to make these assistants more useful. They need to have knowledge about me. They need to know that I have an uncle in Chicago that I could stay at. They need to have knowledge about the world, about the flights, about the weather conditions. Google has a bunch of that knowledge. I wish they would use it a little bit more effectively to help me actually get things done. So, and hopefully what we're trying to do is build the underlying technology to make that possible. Should also be proactive and maybe call my father-in-law and tell them we're going to be late. Right? Kind of thinking ahead, helping me to make my family easier. And this is just one example. Here's a set of other examples. Maybe hopefully you've thought of your own examples of where you'd like the future of assistants to help us in the world. Help my dryer won't turn on. Help me cook a party for a friend's 60th birthday party. My baby hasn't pooed for days. We all have embarrassing health issues that we have. Or help me plan a conference, right? So these are not just about getting a task done. They are about accomplishing tasks, but they're about people. So the assistants are there to actually help people. It's about my family. It's about bringing people together for friends who maybe hadn't seen each other during COVID. Or it's about bringing us together as a research community to network and to build tools. And this is really what we want the assistants to be able to enable us to do. But this is a simplified version kind of where we are today. This is a simplified picture. We have task assistants, social bots, chat bots. And very often what we see here is if we're interacting with Siri or Google, we're often kind of there where we're turning on lights, we're having simple conversations, 1 turn, 2 turns, executing relatively simple commands. But what we want to get to is that assistant that is actually talking to us, helping us perform complex tasks, interacting with the world in new and complex ways. So that's a long-term vision, and I'm going to argue that the way we're going to get there is to make these systems knowledgeable about us and about the world in which they are interacting with. And I come from a background that is search. So I come from an information retrieval background. So I'm going to argue that the knowledge is not just going to be baked into a language model. It's not just going to be memorized, but that it's going to involve search of your information from the web and from external sources of knowledge bases and knowledge graphs, specialized, non-specialized. And so we have to find similar types of information, find people, find contextually appropriate alternatives. And so that's been the history of chatbots, and the history of these assistants has been driven by search, and it will continue to be so, even more so. So let's not forget that history. And we're already seeing this when we actually look at these large-scale language models. So the last talk, we talked about Google, looking at the large-scale language models. Some of the recent one here, this is from DeepMind, work called Retro, where instead of just memorizing a token, instead of just filling in a blank, what they're actually doing is retrieving tokens. And that allows you to have a much smaller language model by actually doing something smarter, by using search. And that's what our assistants and future assistants should also be doing. And if we look at the state of the art of question answering and the state of the art in a lot of these natural language understanding tasks, they're actually using retrieval underneath the hood. So this is called fusion and decoder. And it's not just spitting out an answer from a pre-trained language model. It's using search from a dense vector retrieval to find similar passages, find similar contexts, and using that to generate the correct answer, pulling that evidence together and generating a correct answer. And we know from research that the chat agents and across whole spaces of NLP, this is helping. I'm going to step back in time just a little bit to see where we were, and then I'll talk about maybe where we came from. So we do projects at the university. We sponsor level 4 projects, master's projects. We work with companies who give us data and projects and fun things for the students to work on. And we worked with Monzo. And so we actually worked with them with customer support. So they had a problem where they had to scale their customer support. This was doing knowledge-based retrieval. There's a blog post about some of the work that they were doing in knowledge-based retrieval there. And we worked with them on building test collections. So coming from an IR research perspective, we're very good at user understanding, modeling, evaluation, and kind of principled benchmarks. And this is a very, very simple task where they're just retrieving knowledge bases from the article. This actually works surprisingly well. It's nothing as fancy as what we just saw, but this was a few years ago. So maybe we could actually now generate an answer from that using a language model, incorporating retrieval in that process. But this is still a hard challenge, right? The issue is that some of the things that users are saying, the system needs to ask clarifying questions. The system needs to know when and how to search, and when and how to step in and say, I need more information from you, and get you to the right information. And this is something that still is a challenge for existing systems. And of course, there's a feedback loop because we have human editors kind of creating information, creating knowledge to kind of fill in these gaps, and that can lead to some unintended side effects, kind of retrieving things that perhaps weren't intended as well there. So we have a lot left to do here, but we've come a long way in terms of scaling and automation. I'm going to be talking about knowledge, the role of knowledge. I talked about that as kind of the future of where we want some of this to come from. This is a definition of knowledge from the NLP community, information that's absent from the input but helpful for generating the output. It's a very, very broad definition of knowledge. I come from symbolic systems where that might be a knowledge graph, but it can also just be text, right? So there's been research here. This was from a tutorial, and they actually showed that and demonstrated in the research that if you incorporate retrieval, if you incorporate that external information, the responses are more informative and more useful to users, and users prefer them strongly. So, but if we want to actually leverage knowledge, if we actually want to leverage the different components of this, we have some fundamental challenges that we have to solve. So the first is grounding. This is taking what the user is saying or what the documents say, connecting them to entities in a knowledge graph. So entity detection, entity linking, disambiguation, connecting the pieces of knowledge of what the user said to the structured information that we have. We often think of this as being solved from an NLP side, or there's very little from a research perspective at least. But when we're deploying these systems in the world, we're seeing that actually the entities that matter, the topics that matter to the users, are actually being missed. Right? So we still have a way to go on this. Second is discourse structure, understanding it's not just what users are saying, but the way they're saying it, the trajectory of what they're saying, and how that connects to the knowledge, how that connects to the document structure that they're talking about in the tasks, and the structure of the knowledge base. And very often the existing models that we're using ignore that structure. We'll see some examples of those failures. And then what we want to do is put this in context. So it's not just enough about a single point, but having a guided traversal through a space so that a user doesn't end up in a dead end or a false start, but actually leading them to helpful, engaging, and meaningful trajectory of information and content through those. I'm going to talk about 2 different use cases and 2 different samples of this. The first is in conversational web search from the Trek Conversational Assistance benchmark that I have been leading for the last 4 years now. And the second one I'm going to be talking about is from Grillbot at the Alexa TaskBot Challenge. So if you're familiar with the Alexa Challenge, they had the TaskBot Challenge, and our team won the TaskBot Challenge. And so we'll talk about some of the the ways in which we leverage knowledge to be able to help users to complete their tasks and win that competition. Got to peek behind some of the first people that got to peek behind some of that research. So the first I'm going to talk about is the Trek Conversational Assistance track. This is trying to bring web scale search into a conversation. So imagine if Google would talk to you rather than just having a search box. We can already have a conversation, but it's not embedded throughout the full web scale retrieval. Because right now, very often what we're stuck with is maybe short answer QA. Tell me about the weather. How many trophies did he win? Can you book me this restaurant, maybe? And what we actually want to do is go deeper. We want to have more interesting conversations that are exploratory, that explain the modern scientific method's roots in Aristotle's philosophy, right? To actually be able to teach people information, not just about a single domain like restaurants, but across all of the scope of how you would go to Google. Going to very complex type of language, complex language understanding, and to me, that's some of the benchmark of looking at AI and what we're trying to get at with this benchmark. So TREC is a long-running evaluation search from the information retrieval community run by the US government, NIST. I work in partnership with them, as well as Microsoft Research to be able to build some of this. And instead of simply typing in a search box, it's a chat box where you're typing or talking to the system. It's retrieving information from the web, and then continuing that conversation over a course of many different turns. So it has to retrieve information, read and process the results, and generate responses. And we've seen some major progress over these years. So I'll give you a little bit of a hint of an example of what that might look like. This is a topic, genetic engineering. It was from 2021. And we fixed, for reproducibility, we fixed a conversational trajectory. So we can depend on and evaluate turn-by-turn principled approaches to these ranking. So this is from MS Marco. These results are from the web, from a question answering data set that Microsoft has released. And in this case, how do genes work? A relatively good passage. And there's talking about information about those genes. What other diseases are caused by a single change? This is referring to the last sentence, the fact that sickle cell anemia is caused by a single change. Right? So it has to understand not just what the user is saying, but it has to understand a long answer that is being given, and the search engine and NLP has to understand these long and complex trajectories with each other. It does OK. It gets to a list. So this is a document here, the types of human genetic diseases, single gene, monogenic diseases, and then at the end, it gives a list: cystic fibrosis, Huntington's disease, et cetera. It could do better. We could run this through a generation system, and hopefully it would also omit sickle cell anemia, because we asked for it to say what other diseases were caused, because we already talked about sickle cell anemia. So it should track what I said before and incorporate that into what it's saying next. What are other types of diseases? This, again, performing search. Here's another item in the list. But what we're seeing here is the fact that the search system is just skipping items in the list. Very often, they're looking at individual parts in isolation. They're not undertaking into account the structure of the information or the structure of the knowledge that's being used in a way that is indicative. The user reformulates and provides some feedback. And it does OK, but it kind of skips over. We keep the conversation going. Again, long information, trying to make this challenging to NLP and natural language understanding systems. And this conversation itself here is long. This is approximately 15 different turns, so it's not 1 or 2 turns. If you're just looking at these turns, maybe you can't fully understand the conversation because you need to understand the results. You need to understand what they're talking about. So, no, I meant in humans implies the fact that the previous response from the system was about animals, talking about the impacts of gene editing in animals. So the response not just upon previous turns, but upon previous kind of knowledge information from the system that is being provided. It has to understand discourse. It's going to have to take feedback and understand feedback. No, that's not what I meant. That's too basic. I want something scientific. And the system should respond to these automatically and effectively. And also be able to detect different topic shifts along the way. So I want to give you a peek at some of the state-of-the-art results. These are some of the state-of-the-art systems. Most of these systems, this here, org-conv-dr, is conversational dense retrieval. It's an approach, a research approach that was developed by Microsoft. There was no NLP pipeline. It's just vector composition. I take what you said before, I encode it into vectors, and I use that in vector space to perform retrieval. So that's really starting to be a fundamental shift in terms of how these conversational retrieval systems are working. And if you combine them, again, with a transformer-based ranking model, like was talked about in some of the last talk, that was fine-tuned for ranking, these systems are actually very effective. This in red here is the baseline from the organizers. I want to highlight here some of the best performing systems are all using transformers. They're all using those large language models like T5 large, kind of fine-tuned on very, very large corpora. But we've seen some major breakthroughs here. So year over year, we've seen over 20% improvement in recall. And we've seen overall end-to-end performance effectiveness increase by 20 to 30%. So this is coming from the dense vector retrieval. It's coming from Colbert and the other models that do semantic search in vector space, combined with these transformer-based re-rankers. So these types of models are really transforming the effectiveness of search and the ability to use conversational context. And so this is, quite impressive gains that we've seen. The last one here is actually looking at sentiment analysis, trying to understand the user and human discourse. And it's actually one of the first systems to try to do some of that in this context. I will say that these systems some of them currently still struggle. There's approximately a 30 to 40% difference between what an automatic kind of NLP pipeline that can rewrite queries and do query expansion would do versus what a human would write. And as a conversation goes on, and as those types of discourse and as that structure becomes more and more complex, we're seeing that there's still significant differences and still significant benefits to having additional things in the loop. That's great because it means we still have research challenges that we can tackle in this field. We're continuing this in year 4. This continues to be an ongoing challenge. We're tackling different types of knowledge representations. This year we're focused on generation. People can actually generate responses and they're being assessed, as well as mixed initiative, where the systems can ask clarifying questions, and we're assessing the degree of which, when and how those questions that are being asked are relevant to the topic and relevant to the user to be able to make that effective, and hopefully also a reusable benchmark that's a public resource that companies and people and researchers can use as well. So in the second part, the second kind of use case that I'm going to be talking about, I'm going to be talking about the University of Glasgow Grillbot. So this is some new work. This is the team here, the 5 PhD students. We were the smallest team that was competing in the competition this past year. And it was just announced that the team won the competition. So who's familiar with the Alexa TaskBot challenge? A couple people. Who's familiar with the SocialBot challenge? Okay, a couple others. So I'm going to give you a quick overview here. So it's a multi-million-dollar kind of grand challenge for these systems. The students won over half a $500,000. So this is not a small competition. It's world-leading universities from Stanford, from Carnegie Mellon University, and Glasgow's up there with those universities. And we beat them and the students got a $500,000 prize, right? The history here is the SocialBot has been running for 4 or 5 years. The goal with SocialBot was just to talk. Hey, Alexa, let's chat. And can we have a long-running conversation that spans lots of different topics, keep you engaged. And the goal to keep you engaged was just to ask you questions. What do you like? What's your favorite thing? And to track that across time. So it might span politics, it might span travel, across lots of different domains. And that was an interesting challenge. It's still ongoing. But to me, I want the future of assistance that I talked about earlier to do much more than that. Right? So the TaskBot challenge was introduced this year with the goal of actually helping people do things in the real world. So the domain was cooking. So you have an Alexa device in your home, probably with a screen, as well as doing crafts in DIY. So helping you braid your hair, helping you make origami, helping you do all those types of interactive tasks. So in this case, the agent's goal is to help you work together with you. Hey, Alexa, assist me to actually help me fix a bike or to cook a meal. Right? Particularly for me, the interesting aspect was cooking is quite close to my heart. I also appeared on MasterChef in the United States. And so if the team was going to win, I was going to push them really hard to win for cooking. To leverage cooking knowledge. So I'm glad it worked out. My reputation is still somewhat intact. I'm going to walk you through a couple of the different elements that made our system successful, some of the key kind of technical kind of contributions that we made, and that is still ongoing work kind of to be published. So the first kind of element that I think is really interesting is that we didn't do intents. We built our own system from scratch, all of our own infrastructure from scratch. I'll talk about that in a minute or two. And we built everything from the ground up with a neural-first approach to see how far we could push neural language models. So instead of having fixed intents, what we did was effectively take an approach that was based upon code generation. And so these sequence-to-sequence models can generate code. They can generate natural language code. And so the core part of the system that doesn't just do text classification or intent classification. It generates the action that the system should take next and fills in the parameters that it should take. So it's going to select a step, and it's going to fill in option 4, effectively to make a function call to our backend to pass it that parameter. Okay? So we're doing all of this with a neural language model, sequence to sequence, taking into account the state, taking into account the conversational context. And this was highly effective, much more effective than traditional off-the-shelf intent classifiers that we were using and that we tested from Amazon. How does this work? This works, unsurprisingly, with a large pre-trained language model. So it's a transformer encoder, a transformer decoder. It takes into account the phase, where you are in a conversation. It takes into account the options. So you're passing in the context of what options need to be selected or what the options are, as well as, and that decodes in the decoder what actions it should take and the parameters that it should pass. So this was kind of new, kind of a very new approach to this, and it's something that is part of the open source system that we're going to be releasing as part of this. As we were doing this, lots of different challenges came up, lots of different knowledge challenges came up. If you're going to actually help a user in the world, you have to help them they have to have materials, they have to have ingredients, they have to have actual painting or craft materials. And when we tried any of the off-the-shelf taggers for these, lots of these failed. So we actually didn't use most of them. We need to be able, for the agent to be able to adapt to the user, to be able to halfway through when they're making a recipe or after they've picked a recipe, say, hey, I want to make that vegan. So now we want to do material substitution, to substitute maybe mushrooms for steak or other types of appropriate substitutions, maybe oil for butter, right? Or make it healthy, which in case maybe it should be personalized. That's not something that we were able to do with this challenge, but it should be able to do. And that's an area that we're working on for future work. We also want to support task QA. So if you're in the middle of making cooking, it calls for kosher salt. What is kosher salt? Maybe if you're here, it's not quite as common. It's not in the recipe. You have to go out, you have to find the information that's relevant to the information. That could be web search, but it could also be external, and present it to the user in a fun and engaging way, not just say, kosher salt is blah, okay? And this is the first challenge, the first Alexa challenge that was multimodal. The first time we were able to use a screen to be able to show users information. So we showed them images and video. And hopefully, actually had it be more useful than just looking up a recipe on your phone, right? So that was the goal. So we tried to create and augment the information from these different tasks. So here's just a little use case. Maybe you're searching for something to cook, fall's coming up, so maybe some desserts. I have some recommendations. Maybe I want to make an apple pie, some task search and support. Convince me. So it's not just about finding that information. The language model and the agent has to convince you that this is the thing that you should cook and why you should cook it. So it's by a famous chef, and Bramley apples are in season right now. So that's contextualized knowledge about what type of season it is, et cetera. And then also being able to, as the user is doing this, do stateful question answering. So solid, but I don't have any butter. I looked in my pantry. What can I do? So in this case, do you have some oil? Do you have sunflower oil? It works well in pastries. It doesn't have a very strong flavor. So ideally, it should have a little bit more explanation of how and why that substitution is appropriate. We built something new. We built something called task graphs, which was a new data representation that we looked at for representing the input to a conversation, as well as, so this is for data, so it's not just a series of steps or just a document. It's taking and looking at a representation of all the dependencies that you want to have in the cooking process. So this has conditional nodes, stop nodes. It has connections between the ingredients to individual steps. And what this means is that we can do things. We're not just regurgitating a recipe. When you're reading a step, you're saying, great the ingredients in a bowl. You will need zucchini, shallots, and garlic. So we know which ingredients are being used. We know their quantities, and so you don't have to go back in time. We've done the pre-processing. We've simplified it by making your life easier by actually employing NLP and information extraction to give you this synthesized version. So this is one thing that really differentiated us from some of the other teams that maybe just tried to use things off the shelf. So as I mentioned, we're really trying to go beyond just a series of steps. We built a task graph to be dynamic, to be flexible, to have conditionals, to say if maybe there's a vegan version of this, maybe there's a healthy version of this. It also is scalable, so we had to support both a screen as well as voice-only modalities. So we had to have fallbacks and different capabilities with different nodes that could have explainers. So this is kind of a rich structure for us to be able to represent rich and complex conversations. And maybe down here at the end, maybe additional recipes. So maybe you want a sauce to go with that, or you want some ice cream to go with your apple pie. Maybe you would like to make that. So being able to connect these different recipes together in a way that is natural, flows in the conversation, and is able to help the user accomplish their task. And one of the fun things that came out of this is we thought about system initiative, when and how the system should interact with the user to really help them in the most effective way. So in this case, maybe we can identify that in this step, there's a time for 15 or 20 minutes. We can pre-analyze that and have a timer suggestion, a timer action that's already pre-computed, and say, hey, would you like me to set a timer for this, rather than having the user having to do all of the work. So this should simplify our lives. It should simplify and ask that. So go for it. And maybe, by the way, have you checked on the apple pie? It's been in there a long time. Make sure the crust doesn't burn, right? Because maybe your oven is miscalibrated. We're not quite there yet. So this was really about data. It was about taking data from the web, from YouTube, from WikiHow, from public available sources, from the ones that Amazon provided as well, and doing information extraction, using NLP to get us the right data, to generate the right data for our conversations. So this was preparing for success and then putting that into a search index, having it all searchable so we could search and analyze across the whole corpus of images and videos and recipes to see similarities in real time. So it's not just a task graph corpus, but a search index. That's indexed with dense retrieval as well as sparse retrieval, which is something that made us special because we controlled all of that. So we did a fair bit of augmentation. We used multimodal language models. This is a multimodal task. Most of the recipes that you see, most of the task steps that you see, don't have images, which if you're on a screen, you would like to see a nice image. And ideally, you'd like it to be informative. So in this case, we actually take and basically generate a query for grading zucchini. And we issue that to clip. We retrieve information from a large corpus of images. And most of the time, it finds really great images that are relevant, because usually someone has done a similar step out there before. And so this is an instance of off-the-shelf multimodal language models being used with search and large corpora to really create a rich and engaging experience. And we went further than just images. We went for videos. So we wanted to inform you and educate you along the way in that process by being able to show you short little video clips to maybe how you want to roll the dough, how you want to make pasta, and be able to link that using our task graphs to individual steps. And we have a paper that we just published about some of this work that will be presented at the Web ACM Multimedia coming up. And if you're able to do this well, users really enjoyed it. So users reported learning something new 2/3 of the time if the videos were relevant. And the videos were relevant about 2/3 of the time with the automatic process. So again, the retrieval could be more effective here, but even with what we had, we found that the users were learning a lot and they really enjoyed the short video experience. So just kind of starting to get towards the end, one thing that the team really found was the fact that users would come to us, they would search for things that we didn't have information for. So they come and they search for rice. And we're like, OK, what do we do with that? There is no recipe for rice. Or if you just give a recipe, it's not really what the user is looking for. And so this is a schema. This is simple kind of JSON-like kind of tabular data where you might have a query, a description, trivia, popular dishes, clarifying questions that you might ask the user, maybe some jokes. And then we fed this to a large language model and had it fill in JSON. And so it fills in the queries, it fills in trivia, it fills in clarifying questions. So popular dishes include sushi, fried rice, risotto, and paella. And this information is really able to be served to the user when they have like ambiguous requests. And really, this was one of the key things that allowed us to enrich those task graphs with, there's a joke at this step. So making the task fun for the user. So there's obviously issues around this. Sometimes the jokes don't make a lot of sense, but most of the time they do. And I can obviously have human in the loop to augment this. The performance over the year kind of continued to go up. So you can see here the gains that we made, particularly as we started adding those multimodal features towards the end. I want to highlight that we built everything ourselves from the ground up. We built it using Google scale kind of microservice architectures with gRPC in the engineering background that I had coming from Google, with open source, Kubernetes, kind of Docker, et cetera. So it's one of the first kind of Alexa TaskBot systems to be publicly available, and we're open sourcing it. And we'd love to collaborate on trying to actually make it rich and generalize it to lots of different tasks. So please come work with us on that. The future of that and the future of multimodal systems, the future is going to be multimodal. There's going to be new hardware. We're going to have TaskBots that are going to be with us in the world, whether it's AR, whether it's VR, or something else. That the new hardware is going to be coming out. And so we need to have assistants and platforms to be able to support these interactions. And so hopefully OAT and some of the work that we're doing is starting to lead the way on this. So just to conclude, we really want to see the future of assistants, the future of human and team engagement for web tasks and real-world tasks with flexible and dynamic and engaging ways, leveraging large language models like Palm and others, GPT-3, with a multimodal environment built from the ground up. Using knowledge, using search as fundamental tools in them, and having it all be open source. And that's something that my lab is working on. Oh, I'll just end. We did eventually get to the front of the line. There was a person there. They were very helpful. They helped us to basically book our flight, get us there on time, and gave us a bunch of vouchers. They did more than they had to. And we should expect more from our assistants, just like we expect more from the people and assistants who help us in the real world. So that made my son very happy. So hopefully our future is to have these assistants to enable people, to enable all of you, to cook better, to be able to be better people, to repair your home, so that we can make the world a better place. Please come join us. We're happy to, there's opportunities to partner with us, and we'd love to talk to you. Thank you.